Yeah, hi everyone. My name is Laura Risley. I currently work at ECMWF, but I previously did my PhD at the University of Reading, which I finished late last year. And so I'm going to be showing you some of the work that I did in my PhD. I was supervised by Amos Lawless at the University of Reading, Matt Martin from the UK Met Office, and Anthony Weaver from Surfax. Um, so Okay, so yeah, ocean data simulation is obviously extremely important for several reasons. First and foremost, it can improve forecasts of ocean variables, but also the interaction between the ocean and atmosphere is key to numerical weather prediction. So currently, observations of ocean currents aren't assimilated operationally in global ocean data simulation systems, but this is all set to change as satellites are being proposed to measure these ocean currents. Unfortunately, the operational systems are not equipped to handle these observations due to some of the assumptions that are made about the velocities. And in my PhD, we proposed the use of alternative velocity variables to prepare for these future ocean current measurements. Specifically, we were proposing these variables for use in NEMOVAR, which is the ocean data simulation software used at the Met Office and ECMWF. So our hope is that these alternative velocity variables should lead to improvements in ocean forecasts. So some of the benefits of these alternative variables is firstly, improved estimates of surface currents would be useful for various applications such as search and rescue, oil spill modeling, ship routing, and offshore operations. Secondly, we hope that we can reduce the number of assumptions that are made that are related to the velocities. Additionally, there are velocity observations that can be derived from near-surface drifter positions, giving estimates of 15-meter depth currents. And so our proposed variable should hopefully be also useful for improving the assimilation of these drifter velocities. And finally, the coupling of ocean and biogeochemistry systems is limited due to the fact that ocean data simulation largely inflates the magnitude of vertical velocities. And so these alternative variables that we're proposing should hopefully have give us a better control over the horizontal divergence and as such these vertical velocities. So as I mentioned, there are satellites proposed to measure these ocean currents. If I just talk about ocean observations in general quickly, we have various in situ measurements taken in the ocean ranging from mammals to ships. And although the global observing system on the top right looks like there are plenty of observations, they're actually quite sparse. And there are regions in the north that are nearly completely unobserved by in situ measurements. So then we also have satellite observations of the ocean, but these can only cover the surface. Now, if we think about horizontal velocities in particular, these are unobserved globally, but there are sparse observations that come from high-frequency radar and also those drifter velocities, but these are not used in global data simulation systems. So there's been multiple missions proposed to measure these velocities directly, such as Harmony and some other missions. Unfortunately, from this list, Harmony is the only mission that is actually sent to launch. But these proposed missions highlight the demand for these ocean current measurements, and so we need to improve the current ocean data simulations for these velocity measurements. So my PhD aimed to answer the following questions. What are the implications of using alternative velocity variables in variational data simulation, in particular NEMOVAR, and how do these variables respond to the assimilation of velocity observations? So just a quick bit of background. In variational data simulation, as I'm sure most of you know, model variables are transformed to control variables, and these are assumed to be mutually uncorrelated in the background error covariance formulation. So in particular for NEMOVAR, which as I said is the data simulation software we use for the NEMO model, which is used at the Met Office and ECMWF. In NEMOVAR, the velocities are transformed to their unbalanced, so their ageostrophic components using geostrophic balance. And these are used as control variables. Now, the ageostrophic components of the velocities are highly dependent on each other. And therefore, the assumption of these being mutually uncorrelated is incorrect. And this would lead to a suboptimal simulation of future ocean current measurements. And so we seek an alternative alternative velocity control variables in NEMOVAR. So we propose using Helmholtz theorem. So Helmholtz theorem splits the velocities into their irrotational and non-divergent parts. These are velocity potential and stream function. Helmholtz theorem is used commonly in atmospheric variational data simulation, but as I said, it's not used in NemoVar. So what we propose is we apply an additional transformation from the ageostrophic velocities to ageostrophic velocity potential and stream function and use these as control variables. Now, these control variables not only satisfy the uncorrelated assumption more appropriately, but they would also give us a better control over the horizontal divergence, so these vertical motions. And as we said, that would be beneficial. So in my PhD, we tested these proposed control variables using the NemoVar framework. So we performed assimilation experiments in NemoVar, specifically using the gyre configuration of NEMO. So the gyre configuration uses the primitive equations to simulate the seasonal cycle of a double gyre box model on a beta plane with analytical seasonal forcing, bounded by vertical walls and a flat bottom. And we're representing an idealized North Atlantic basin. So we're eventually developing a westerly boundary current and the Gulf Stream. And it's initiated at rest. And these are just some plots here of some of the model output after this the gyre configuration has been spun up. So I set up cycling twin experiments in NemoVar. So for these, we have a nature run, which is a high resolution model run that we consider to be our truth. And this is was at a 1/36th of a degree resolution. We then ran multiple assimilation experiments, and these were initialized at a lower resolution, so a 12th of degree resolution. We had a daily assimilation cycle and a 1 year long experiment. And here I'm just showing a diagram of how we spun up the gyre configuration. As I said, it's initialized at rest, and so we had to spin this up for a number of years to generate some more realistic small scale features. So for the observations, we simulated these observations from the nature run by adding Gaussian noise to the nature run values, and we used the times, dates of year, as well as the location of the real observations used in the Met Office foam system for 2016, but the values were simulated from the nature run. For all of our experiments, we use the standard observation types. So we've got in situ temperature and salinity profiles, sea surface temperature observations, and altimeter observations. And the top row of plots show the standard observation types, with the left plot being the temperature profiles, the middle being sea surface temperature, and the right the altimeter observations. Now, some of our experiments have the addition of new velocity observations, which might be obtained from a SkimLight satellite mission. So the plots on the bottom, the left is U and the right is V, and these show a one day of what these synthetic observations where they would look like. Okay, so I ran 5 experiments. The first was a free run, so we started from our lower resolution initial conditions, but obviously no assimilation. Then I ran 2 control experiments, both of which used the ageostrophic velocities as the control variables. The first control experiment used just the standard observation types, but the second control experiment is where we added in these velocity observations. I then ran 2 additional experiments with our new control variables, so with the ageostrophic stream function and velocity potential as our velocity control variables. But the difference with the second experiment is that we have set the standard deviation of velocity potential to be 0. So as you will recall from the beginning of my experiment, my presentation, the coupling of ocean and biogeochemistry systems is limited due to the fact that ocean data simulation inflates the magnitude of these vertical velocities. And so the theory is that by setting the standard deviation equal to 0, we are removing the ageostrophic divergent component of the velocity from the analysis increment, and as such would be removing the ageostrophic component of the vertical velocities. And so overall, we would hope to reduce the magnitude of these vertical motions. So I'm going to present to you some of the results we got from these experiments. So firstly here I have plots of the mean absolute error of the assimilation experiments compared to the nature run. This is plotted against time, averaged over the domain, and here I have the errors for the zonal velocity and meridional velocity at the surface. So here our blue line is the free run, our orange is the first control experiment with standard observation types, green we have the additional velocity data, and red and purple are our new control variable experiments. So it's clear to see here that the free run is the worst, which we hope and expect it to be, and that comes very closely second is the first control experiment. We see a very large improvement in the errors with this additional of velocity observations. So this is obviously positive because it's showing that hopefully these future satellite missions that will measure these future ocean current measurements would greatly improve the analysis produced by our data simulation systems. And finally, we have our experiments with the new control variables. So both the purple and the red line, we can see in places these actually add to a further improvement. Overall, they perform either better or very similar to our previous control variables with these new velocity observations. So here we're providing plots for the same experiments, but now I'm showing sea surface height, temperature, and salinity. So less obvious with temperature, but for sea surface height and salinity, we see a very similar picture to what I showed on the previous slide. Introducing these velocity observations improves the error by quite a bit, and the introduction of our new control variables show considerable promise. It's worth noting at this point that we did not perform extensive tuning of the background error statistics, and so all these improvements that I'm showing in these slides, we could only hope for a even further improvement if we were able to perform more refined tuning of the background error statistics. So our new control variables look like they're making a positive impact, but we can definitely say that the velocity observations are improving things. So the next question is, do our new control variables help with these vertical motions? So we looked at the effect of the variables on these vertical velocities by looking at the spatial mean of the absolute values, because remember we're concerned with the magnitude of the vertical velocities. So on the left, I show the full vertical velocities output from the model. So this is across the depths, averaged over time in the domain. So you can see here quite dramatically how the assimilation process inflates these vertical motions as the free run has such reduced velocities compared to the assimilation experiments. Unfortunately, the addition of our new control variables, especially with the ageostrophic velocity potential part removed in our purple line, has not reduced these vertical velocities at all. So our next step, we thought, looking at the diagnosed vertical velocity increments. So instead of looking at the full field that's produced from assimilating these observations, what happens if we diagnose the vertical velocity increments directly from our horizontal velocity increments, including both the balanced and unbalanced components? And so you can see this plot on the right, and although it's a very small improvement, you do see that this removing the ageostrophic component of velocity potential has reduced the magnitude of these vertical velocity increments. So why is this? So we looked into this a little bit further. So the plot on the top is, again, these plots are for the experiment where we've removed the ageostrophic component of velocity potential. And the bold line in purple is what I showed on the previous slide, our diagnosed velocity increments. And the dashed line is the difference between the vertical velocity before and after the assimilation. So we can see here that there is a strong discrepancy between the increment that we've diagnosed from our horizontal velocities and the increment that's produced from the assimilation process. And so this discrepancy suggests that the model is continuing to generate these spurious vertical motions. In particular, it implies that the balance component of the vertical velocity is playing a dominant role in determining the total velocity, vertical velocity magnitude. Just to highlight...
1 minute of normal time, sorry.
Pardon?
1 minute of normal time.
Okay, yeah, that's all right, thank you. Yeah, so just to kind of show this discrepancy, to highlight this discrepancy even further, the plots on the bottom are zonal and meridional velocity. Again, we've plotted the same thing. We've plotted the increments that we have got from the data simulation, the increments after we've applied the IAU, and these increments are very similar in magnitude. So it kind of highlights that the model is really causing these inflated vertical velocity vertical velocity magnitude. Okay, so just to summarize, we've introduced some new velocity control barrels for use in NemoVar. And from our simulation experiments, we've been able to show that there is really good impact from velocity data simulation, not only improving the horizontal velocities, but also there's a good impact for sea surface height, temperature, and salinity. Our new control variables show considerable promise, and they can also lead to an improved performance when simulating this velocity data. And this improvement should hopefully only be improved further with some extensive tuning of the background area statistics. Now, our proposed control variables do seem to reduce the magnitude of the diagnosed vertical velocity increments, but the model is still introducing these spurious vertical velocities during the simulation, indicating that the balance component of the vertical velocities is playing a dominant role in determining these total vertical velocity magnitude. And so further work is needed to improve these as part of the NemoVar balance operator. So we've demonstrated the potential for improving the simulation of future ocean current measurements using our proposed control variable transform. And thank you so much for listening.
Yeah, thank you. Feel free to type questions into the chat document, that Lars has been sharing. But I've got a question. I'll amaze and surprise you. I've got a question. So the question is, so the gyre model, is it just got a flat bottom? Because I was wondering what the impact of having a more realistic might be on the performance of these new velocity control variables.
Yeah, so it does have a flat bottom. It would have been nice to see, I guess, the effect on something a little bit more realistic. I don't have any theories of what would happen. I guess because we were mainly looking at the surface, but I'm sure there might have been, especially some effects maybe with the vertical velocities, because the depths were quite, because obviously like the change across the depths was a bit more dramatic. But I think with all of this work, we've looked at obviously the gyre configuration, which is a nice idealized basin, but it would be really good to further this work to more like a global model or something, with some bathymetry.
Thank you. So I've got another question coming in from Alex Kurapov, and he says, separating the velocity field into the two components, rotational and velocity potential, I think it was. Do you need to set up the boundary conditions for that, and what are they?
Yes.
So I think this model has closed boundaries, doesn't it?
Yeah.
But in general, you would have to.
Yeah, there was quite the first part of my PhD is basically all looking at the boundary conditions for these variables, because it's the reason usually velocity potential and stream function aren't used in the ocean is due to the complexity of the coastal coastal boundaries. And so what we actually did was avoiding setting boundary conditions altogether. So in my first chapter, we discussed moving. So because we use an Arakawa C grid, we actually move stream function to the center of the grid so that we don't have to set any boundary conditions. Because that's part of the problem is with these boundary conditions and these variables. So for stream function, we've avoided setting boundary conditions for this how we set this up.
Yeah, thank you.